Hi, I'm David Bonsack, Product Manager for Rheology at TA Instruments. I'd like to welcome you and thank you for joining us for today's webinar. During the webinar, you can customize your viewing interface by arranging the windows to your liking. You can resize video and slide windows independently from one another by clicking and dragging at the bottom right-hand corner of each window. If you get disconnected at any time, please use the instructions you've received to log back in. You can access several different content windows by clicking the widgets at the bottom of the screen. These include speaker bios, additional file downloads, and social media interactions. If you need help, click the question mark widget. Please ask any questions you may have at any time during the presentation by submitting them through the Q&A window. We will answer as many as possible of these at the end of the webinar. Our guest speaker today is Dr. Alina Latshaw of TA Instruments. Dr. Latshaw is an applications engineer with TA, where she supports customers in the areas of rheology and dynamic mechanical analysis. Prior to joining TA, she completed her master's and PhD under the supervision of Professor Saad Khan at North Carolina State University, where she developed novel methods to improve throughput in electrospinning processes and used rheology to characterize the curing processes of several different chemistries. It is truly a pleasure to have Dr. Latshaw with us today. The title of her talk is Tribo Rheometry, quantifying friction between surfaces using rotational rheometers. Alina?
Thanks, Dave. Hi, I'm Alina Latshaw, and today we'll be talking about Tribo Rheometry in a way to quantify friction between the surfaces of your rotational rheometer. In this presentation, we'll be discussing the theory behind tribology, introducing the Tribo Rheometry accessory for the rotational rheometer, and then going through a few case studies that we've performed in-house and discussing some of the data that we can get from these types of tests. Now, the word tribology can be derived from two words. The first word being tribos, which is Greek, meaning rubbing or to rub, and then the suffix ology, which is literally the meaning the study of. So when we put these words together, tribology literally means the study of rubbing or the study of things that rub. So this can include properties such as adhesion, friction, lubrication, and wear. Another way to think about it is tribology is the study of friction, wear, and lubrication between two interacting surfaces while they're in relative motion with one another. Now, we experience this phenomenon every day, whether it's between the gears in your car engine, the brake pads on your car when you're braking on your way to work, or even applying cosmetic and personal care products onto your skin to moisturize your skin. Whether we're chewing food or drinking drinks and the mouthfeel in our mouths, or even in artificial joints for prosthetics, which are designed to mimic the feel and the movement of natural joints. Some of the aspects of tribology will then include studies such as friction, or the forces between these moving materials and these moving surfaces, things such as abrasion, whether these surfaces will undergo any type of surface damage while they're moving past one another. These tests can also be done in either dry or lubricated conditions, so solid or liquid lubrication, also lubricating between oils versus greases and different kinds of formulations. Another aspect of it is going through and studying the influence of surface modifications and coatings and how that affects the coefficient of friction between two types of materials. Now, taking all of these aspects, tribology will then be related to a product performance, its reliability, its wear, so how quickly do we need to maybe replace these oils and greases, how quickly do we need to replace gears, for instance, or these two surfaces, and then also in some newer areas in the food and drinks industry, things such as mouthfeel, how a consumer perceives a product when they're consuming it, or even tactility, so how these personal care products or things feel to us on our skins. The way that we measure coefficient of friction, or the way that we quantify it, is coefficient of friction, which is mu. And the way that we do this is we take two surfaces and we put them in contact with one another and push these surfaces together through a load force, so the force that's moving perpendicular to the motion. And then we're going to move one of these plates and we're going to kind of slide them past one another. So now one of the surfaces will have a direction of motion. They're going to be pushed together in contact with one another through the load force, and then some frictional force is going to oppose the motion that one of our surfaces is going through. So again, in between these two surfaces, as you can see in the diagram. So the coefficient of friction is just simply the frictional force divided by the load force, or you could think of it also as the ratio between shear stress and normal stress. Now, if we zoom in on all of these surfaces, right, so on a macroscopic scale, things such as stainless steel or polymer bars, they look really smooth on the macroscopic scale. But what we're studying with tribology is the interactions on this microscopic scale. So if we zoom in between these surfaces when they're in contact with one another, you'll see all of these surfaces are somewhat rough on a small length scale, so maybe microns, nanometers even. And all these roughnesses in the surfaces are known as surface asperities. Every material will have its own unique characteristic of the surface asperities, and it will depend on things such as the composition of the material, also the way that these materials were processed, for instance, things like that. So when we push these materials together, we're looking at the interaction between these surface asperities. When we have a small load force, for instance, these surface asperities may not be interacting with one another too much, but it's still something to consider. So you can see in the larger diagram, those surface roughnesses they're interacting, but maybe not all of them are participating in the interaction. However, if we increase that load force and now we push these materials together even further, now you could see in the large load force diagram, all of these surface asperities are starting to be in contact with one another. Another way to think about it is if you have in your room, say you have a small mouse and then you have a really large elephant on your carpet. So you could think of the carpet fibers as a surface asperity, right? So there's a little bit of roughness on them. Now when we have the small mouse on the carpet, it barely touches it. You don't really see the carpet fibers move or flex at all because they're not really being interacted with one another or with the surface of the mouse. However, if you have an elephant, which would represent the large load force, you can always see those carpet fibers are going to kind of compress with one another. Now, surface asperities may not compress, but they're still interacting with the other surface. So how do we put this onto a rheometer, right? So we have these surfaces. Again, these plates come into contact with one another, so we need to control the force between them, and then we're going to also apply movement to one of the surfaces. So an accurate tribology measurement will require that we have direct contact between these two interacting surfaces. So we need to have a way to control and apply the load force. In the rotational rheometer case, what we're doing is we actually have the load force acting in the axial direction, and then when we're moving one of the surfaces, a rotational rheometer will have the movement be in the rotational direction. So again, as you could see in the diagram, we have the load force in the axial direction, and then the movement's going to be in the rotational direction. Now, the other aspect of an accurate tribological measurement is going to be relative motion between the two surfaces. So again, in a rotational rheometer, this would mean we need to have excellent angular velocity control, or the movement in the rotational direction. So again, all of these things, whether it's axial force or angular velocity control, we already control and apply these on our rotational rheometers very well, just for our simple everyday rheological measurements. And so it just made sense to bring this tribology accessory into our rotational rheometers. The thing we need to consider is now we need a way to provide good alignment between these two surfaces, because as I mentioned, we have these surface asperities which are not uniform throughout all of the surface, but we want to make sure that we uniformly distribute that load force between all the surfaces in contact, not only when it's standing still, but also when we're rotating or when they're moving past one another. And as these surface asperities move past one another, we're going to have different length scales, if you will. So we need to provide a way to make that axial force uniformly distributed. The way that we do that in our Tribo Rheometry accessory is by adding what we call the beam coupling. Now you could see in the picture, for instance, it's exaggerated, for instance, but you have your bottom surface, which may have a little bit of surface asperities, and then you have your top surface. In this case, it's depicted as a ring, but you could see that the spring or our beam coupling allows these two surfaces to stay in contact with one another, uniformly distributes all of that axial force between all of the modes of contact, while also providing that while we rotate. So what this beam coupling does, as you can see, we offer a stainless steel coupling and an aluminum coupling, but what it does is it introduces axial compliance, so compliance in the axial direction, without compromising anything in the angular stiffness. So we want to make sure we have excellent control and excellent stiffness in that rotational direction so we can make that torque measurement and hence the frictional measurement. But we also want to make sure that there's a little bit of compliance to make sure that our surfaces stay in contact and don't lose contact with one another and then move up and down like this. We want to make sure that everything's always in contact with each other. So the helical spring that we use in our beam coupling ensures this good alignment between the two surfaces. And then it's also a self-aligning coupling. So as we're rotating and as things are changing a little bit throughout our experiment, the coupling will self-align and it will provide that smooth axial force control while maintaining the angular stiffness. Some things to know, as I mentioned, we do offer two. It comes in the kit. We have the stainless steel coupling and the aluminum coupling. The stainless steel coupling, since it is stiffer, we do recommend using it for axial or for load forces greater than 6 newtons. But since the aluminum coupling is a little bit softer, we recommend nothing greater than 20 newtons. Now, all of this accessory is compatible with all of our DHR rheometers and our Aries G2 rheometers. We can have temperature systems and temperature control with either the Peltier plate or advanced Peltier system, and the ETC oven or the FCO oven. The temperature ranges can go from -150 all the way up to 350, so if you're doing such studies such as mouthfeel or body temperature, we have control up to that temperature, or if we're doing studies at elevated temperatures, we have the ability to do that as well. The maximum axial forces, as you can see, will vary based on the instrument, but the maximum torque that you can apply is still 200 milliNewton meters in torque. All of these variables, so all of the tribology related variables are going to be directly incorporated into the Trio software. Clearly for you, things such as sliding speed, the sliding distance, the load force, the friction force, coefficient of friction, and the Gumbel number if some of the information is applied. But all of those will be supplied within Trios and calculated directly for you. Now, our accessories come in 4 flavors, if you will. We have the 4 different geometries. We have the ring-on-plate geometry. As you can see, we have a ring, and then it's in contact with a bottom plate or a bottom surface. Also, the 3 balls-on plate, which on the top, instead of a ring now, we have 3 hemispherical spheres and the plate on the bottom. And then on the other one, you also have a ball on 3 plates. So you can have a ball, and then the 3 plates are at an angle with the sphere. And then you can also have the 4 balls, which has 1 sphere on the top and then 3 spheres on the bottom. Now, if you notice, all of these have a modular design. So what that means is that it's easy to switch back and forth between the different geometries depending on what types of materials you're studying. It's an easy method to interchange them. All of these tests can also be performed in dry or lubricated conditions depending on what's of interest and what the application is. And then the last thing is that the geometry surfaces can be easily customized. So all of these are standard stainless steel, but if you have things such as skin mimic or papillae, like on the tongue, for instance, if you want to do mouthfeel, or if you're studying prosthetics, then maybe you're looking at some coatings, coated materials, or even polymers. You can customize the geometries as you see fit. So what we're going to do now is we're going to go through each individual geometry, kind of give you a little bit more specifications and some more information about them. So first up is the ring-on-plate geometry. As you can see, we have these. You can have a full ring. If you flip it upside down, you can even have a notched ring, or what we call the half ring. So what this half ring allows is the notches allow for some low viscosity lubricant to continually flow and coat the substrates during the test. So if you're studying anything with lubricants, notched ring's really the way to go. Because we have a defined geometry or defined dimensions of this ring, we can actually calculate out the stress, the frictional stress. So again, there's the defined contact surface area, so you can calculate friction and normal stresses. And this geometry is really best suited for softer substrates because of this large contact area and the wide diameter. It's just a little bit easier to control. The way that you would customize this geometry is simply to adhere or attach, maybe using double-sided tape. You can attach anything to the bottom plate or cup, whether you have lubricant, then you have a cup so the lubricant doesn't fly off everywhere. Or you can adhere it even to the surface of the ring and put those materials in contact with one another. Okay, but the thing to keep in mind is that in this case, because our surfaces are perpendicular to one another, the load force is going to be equal to the axial force that we're calculating. On the 3 balls in plate geometry, now again, we have 3 hemispherical balls on the top, and then it's going to be in contact with a plate at the bottom. So these upper spheres provide point contacts with the bottom substrates. Because it's a point contact and we don't know the actual full contact area, we don't automatically calculate stress, although if you wanted to and you wanted to go through and figure out what the contact area is, you're more than welcome to calculate out the stress yourself. But this material, or this geometry, is better suited for hard and stiff substrates because of that point contact. It's easier to not max out all that axial force. The way that you would customize this geometry is simply by attaching any type of substrate to using double-sided tape to that bottom plate or that cup again. If you can find some threaded hemispherical spheres, you're more than welcome to attach those to the upper plate as well. For the ball on 3 plates geometry, it's a little bit different. You can see here we have a cup where the 3 plates are actually situated in at an angle. And then the upper geometry has a chuck where we can place a 1/2-inch diameter sphere. Now, this upper sphere, again, will provide point contact between the 3 different plates. So again, it's a point contact, meaning we don't automatically calculate out stress. But because of that point contact, this is really great for hard and stiff substrates. This geometry is also very good if you have lubricants that will flow under gravity, because since it is at an angle, the lubricant will always flow back in to, again, fill in that point contact, ensuring that there's lubricant throughout the entire test. The way that you would customize this one is if you have a stiff substrate, you can choose 2 different ways. If you have a stiff substrate and rectangular plates, you can actually machine them to fit instead of the stainless steel plates that come standard with this kit. You can place them in and replace those plates with types of polymers if you want. Or if you want, you can also order 1/2-inch diameter spheres and simply replace the stainless steel sphere in the upper geometry. So this is a really great way to customize the geometry setup if you have multiple types of materials, such as like a titanium sphere, for instance, onto maybe a coated polymer plate for any type of prosthetic testing. And lastly, we have the 4 balls geometry. So again, it uses the same upper chuck. It uses a chuck to hold the upper sphere, and then the bottom will have 3 spheres, in a container. So they're all arranged in triangle pattern with one another. Again, this upper sphere will provide that point contact with the bottom spheres, and this setup is actually really great for lubrication testing. This has also started being used in some asphalt testing as well. So there's that. The way that you would customize this geometry is simply by replacing those 1/2-inch diameter spheres with other spheres very similar to what I just spoke about on the ball on 3 plates geometry. Again, it is important to mention when using this specific geometry, all of the spheres should be tightened so that they're held in place and don't roll. We just want these materials sliding past one another. We don't want them to be rolling necessarily as well. So when we think about the coefficient of friction, we've talked about, we have this load force, we have the sliding velocity that can affect the coefficient of friction, we have these different materials, their surface disparities, and there's a lot of different categories or different parameters that can start affecting the coefficient of friction. What I've done here is I've actually kind of categorized them into 3 different areas. So one of which would be the surfaces themselves will play a really large role in the coefficient of friction. The surfaces, you can change the materials of construction, or the modulus, which would again change the modulus of these materials. So things such as plastics versus metal versus maybe a skin substitute, they're all going to behave very differently than each other. And so the materials of construction is something to consider of what mimics your application the most. Also, the roughness of the surfaces. So what's that size scale of the asperities? Are they really small? Do you have a relatively smooth surface? Or is this a surface that's actually quite rough? Because again, that's going to start playing a role in things like abrasion and the coefficient of friction. Also, do we have a coating? Is there a coating on these surfaces? If we do, what kind of coating is it? What's the material of the coating? How thick is that coating? Things like that are going to play a role in the coefficient of friction. And then also the lubricant properties, so things such as the viscosity of that lubricant, the formulation of that lubricant, what's going to happen. Now when we talk about the test parameters, we can define things such as the sliding speed, so how quickly are our surfaces sliding past one another, what temperature is this test being performed at, and then what's the load force, so how much force are we applying when we push these two surfaces together. And then lastly, you can also look at the geometry. So we've talked about 4 different geometries. What kind of area of contact do they have? Is it a point contact? What is the geometry of that contact? And then what's the contact stress? So all of those will play a role in the coefficient of friction. So as you can see here, specifically when we talked about the different surfaces, the coefficient of friction isn't just any type of property, it's a system property. It will depend on the geometry that you've chosen, the test parameters, and then even just what kind of surfaces that you've chosen to do this testing on. So that's definitely something to keep in mind, is that it is a system property. So when we change materials out, we would expect the coefficient of friction to change. So what are some things to consider when we're doing this coefficient of friction testing on this Tribo Rheometry accessory? Well, first of all, again, we've talked about the wear and the friction is going to depend on the chosen surface materials and the system that we're studying. And by system, I mean the geometry that we're studying. So we can look at the coefficient of friction as a function of the angular velocity, the sliding speed, what kind of torque are we applying. So again, angular velocity would be how fast are we rotating, which will directly relate to the sliding speed of your materials. And then the torque, how much torque is applied when we're rotating these surfaces past one another. And so when we're designing a test and we're trying to figure out what to do, these are all the things that we need to keep in mind and decide ahead of time while we're doing these tests. The coefficient of friction will also heavily depend on the load force. So sometimes like, well, what load force do I use? I'm not really sure what I'm doing. And a good approach is really to choose the load force that simulates the type of application that you're doing. So for mouthfeel applications, we typically tend towards lower load forces, so they'd be like 1 to 3 newtons. Or if it's something like greases and oils and engines, maybe we're looking at more of a heavy load because we want to see, because those gears are really going to be compressed against one another. So these are all things to keep in mind. Now if someone's interested in studying the wear patterns on some of these softer substrates, that can be analyzed externally. So after you run your test, you could take these plate surfaces and then look at them through a microscope to see what the surfaces look like before and after the testing, to see what the wear patterns are, or how much of the surface has been worn down. And then one last thing is if we are operating at very high temperatures at these really high rotational speeds for a long period of time, then we can consider using motor cooling. And if you're not familiar with motor cooling, just check out our Trios online help. It will tell you how to set everything up.